All right, welcome back. This is our video solution to problem 2 from Quiz 5, Spring 2023, Math 302 at Cal State Fullerton. And here, we've done the Euclidean algorithm, right? It's been done for us. We're given two numbers, 22 and 17, and the Euclidean algorithm tells us that the greatest common divisor is 1. Probably you knew the GCD was 1 anyway, because 17 is prime, but we got it here. Now, one of the cool parts of Bézout's lemma is it tells us we can write the GCD, in this case 1, as a z-linear combination of the two inputs, in this case 22 and 17. And there's of course many ways that you could try to find that z-linear combination, but the extended Euclidean algorithm is going to give us what we call the canonical Bézout coefficients, right? From which we can get all other possible coefficients. All right, so we're going to do it. Now, I'm going to do it in two different ways. The first way is a variation of the more standard way, and then the second way uses an algorithm that I developed personally. So the first way, I'm going to use some notation. One of my former students came up with, Natalie Medina. So what she likes to do is to give names to these two numbers. All right. And the way she comes up with her notation is, well, typically we're writing down something like AU plus BV. This seems to show up in all of the books, right? They like to use U and V. And so she found it hard to keep track of, did A go with U? Did A go with V? Which one went with which? And so she said, well, let me just take the A and write it as an N. Okay, and why? Well, because it's just an upside down U, right? Maybe reflected a little bit. Okay, and the B, she does the same thing. She's going to turn that over, and she's going to make a little wedge symbol. Okay, so in this case, we might take the 22, and we could write that as N, and the 17, and we're going to write that as the wedge symbol. Okay, so that's what we're going to do. Okay, so that's step 1. Step 2, we're going to solve each line in the Euclidean algorithm, right? So up here, we're going to solve it for the remainder. All right, so solve for the remainder while writing in terms of n and wedge. Okay, that way we don't have to keep track of the 22 and the 17, which can be useful sometimes when those numbers get used both as the divisor or the dividend and as a quotient, right? So this avoids this issue. So here we go. We're going to start from the top line, and I'm going to solve for the remainder. And I'm going to write 5 is equal to, well, it should be 22, but I'm not going to write 22. I'll just write n minus 1 times wedge. Okay, that was the 17. Okay, now I go to the second line, and I get 2. 2 is equal to, okay, 17 is my wedge, minus 3 times 5. Okay, but now instead of the 5, I can use the previous line. 5, we know, is n minus 1 wedge. And let's just simplify at this point. So first, how many n's do I have? Well, I have minus 3 times n. And then how many wedges? Well, I have 1 wedge. And then minus 3 times minus 1 is plus 3 wedges. So 1 plus 3 is 4 wedges. All right, now I go to the bottom line. 1 is equal to, let's see, it's going to be a 5. But we already know 5 is n minus 1 wedge minus 2 times 2. And 2 is negative 3 n's plus 4 wedges. And now we can simplify. We count how many n's. So let's see, here we have 1 n. And then over here we have minus 2 times minus 3 is 6 n's. So 1 and 6 is 7 n's. And then how many wedges? Let's see, we have minus 1 wedge. Then we have minus 2 times 4 is minus 8. So minus 1 and minus 8 is minus 9 wedges. And so this bottom line tells us that we can write the GCD1 as 7 times n, which is 22, minus 9 times wedge, which is 17. Okay, let's see, does this check out? Let's see, 7 by 22, that's 154. And 9 by 17, that's what, 153. Yep, 154 minus 153 is equal to 1. Okay, so that's the Medina method. All right, the Glesser method, which you can find in one of the other videos in this playlist, we're going to take the quotients from the Euclidean algorithm. Starting from the bottom, we're going to write them down, 2, 3, 1, and we're going to put a negative in front of each. Then I'm going to put a 1 underneath the first term. I'm going to copy this first term in the next place. And now here comes the real algorithm. I multiply down and add to the left. So negative 3 times negative 2 is 6, plus 1 is 7. Now I do it again. Negative 1 times 7 is negative 7, plus negative 2 is negative 9. And these here give me my canonical Bézout coefficients, 7 and negative 9, which you see are precisely the numbers that we got using the Medina method as well. All right, and you want to use them in the same order, right, that you started your Euclidean algorithm with, right? So the 7 corresponds to the 22, the negative 9 corresponds to the 17. All right, there we go. I hope this is enlightening. We'll see you next time.